Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 35, we will learn about landfill design, part 3, and here we will learn about determining the size of landfills. So, the concepts that we will cover are on landfill volume and site life, shredding and baling, typical sanitary landfill site plan and facilities. We will learn about landfill phasing. We will give a typical example of a landfill design. Then closure and rehabilitation of old dump sites, how to do that. Then preliminary estimation of landfill capacity, height and area. And then we will show you some examples of problems and then some case studies. So, landfill volume and site life is what as a planner is most important, that is what we need to determine. We need to determine the area that we require for that particular landfill. And that has to be determined for estimation of landfill volume. So, area of the landfill or landfill volume, that has to be ascertained, and also this will give us an idea about the site life of that particular landfill. So, this is determined based on the quantity of solid waste that is generated over the design period of the landfill. Sometimes we can design the design period based on land area available. Alternatively, if I know that I have to have a landfill which will work for so many years. So, in that case, we have to determine a land area or proper site where we have the adequate land area. So, in any case, we have to estimate the total landfill volume and the area required for it. Then, compacted density of waste for the kind of waste that is generated in that particular area. Volume of cover material to be used during the life of the landfill, because as we have discussed earlier, this sometimes determines the life of the landfill. If soil is not available, it would be too expensive to import soil from outside. Allowances for expected settlement. A lot of settlement happens over the life of the landfill. That has to be considered. Like we said that the average density is around 1 ton per meter cube. But during the initial life starting period, it is 0.8 to 0.85 tons per meter cube. Whereas in the final, you will see around 1.2 tons per meter cube. That becomes the density, right? The site life is based on volume of cover material or soil or the amount of solid waste that can be adequate covered by the volume of covered material available on the site. So, this could be one of the criteria for determining the site life of that particular landfill site. Settlement occurs over the entire life of the active, it occurs during the active life of the landfill and also later on as well to a certain extent, but less. And it adds to available capacity of the landfill. That means if the total volume is something, because of settlement, we will have additional volume available. That needs to be considered. So, the extent of settlement, how much settlement will occur depends on initial compaction. If the initial compaction is low, then settlement would be higher. Characteristics of the waste, if we have a lot of organic waste and other material which decomposes and becomes gas and other, breaks down into other materials, then of course, compaction would be higher. Degree of compaction, how much I compact. Consolidation from leachate and gas formation. So, how much amount of leachate is formed, how much amount of gas is formed. That also gives us an idea about what should be the settlement of the entire site. About 90% of the ultimate settlement occurs within the first 5 years. So, settlement keeps on happening over the life of the landfill and even after that, but 90% of it happens within the first 5 years. Then we will talk about shredding and baling. Before waste is taken to a landfill site, we can further, process it, or, we can reduce it, or we can organize it, you can say, right? So, shredding and baling are these two techniques involving preparation of refuse prior to landfilling. Now, if the waste is shredded means we make it into smaller pieces. We have discussed some of it earlier as well. And baling means, compacting the waste into some volume, which is like maybe a rectangular block or a, squarish block and with higher density. So waste can be baled by compression into large rectangular blocks with densities up to 1000 kg per meter cube. So that is how we can do first shredding and then baling, which helps in organizing the waste in compact units which could be stored into the cells of the landfill site. Waste after shredding reduces to particle size less than 2 to 6 inches by mechanical processes such as cutting, tearing, ripping and impact shattering. Right. So these are the mechanical processes that could be taken up to shred the waste into smaller sizes. Shredded waste can be compressed to a greater density than unprocessed waste by about 25%. What it means? That means it will increase the capacity of the landfill by 25% if I adopt shredding and baling. So obviously that's in areas where land is very short or land is available only at a very high premium, we can go for shredding and baling of waste. Shredding also, because we are making it into smaller pieces and all, it helps in decomposition faster. It reduces the daily cover because there would be lesser things sticking out of the waste because everything is small size. So the cover could be given uniformly. So reduces the daily cover. It reduces blowing of paper and debris from the waste. It also results in higher methane and leachate production because of more decomposition. So that is why before even we bring the waste or we put the waste into the active landfill site, we can adopt these particular measures. So this is how a landfill site looks like. So just you can see there are phases, phase 1, 2, 3. We have discussed phases earlier, but we will discuss it further. So these phases are designed, that means the entire volume that is required to be stored, or waste that is entire volume of waste that needs to be stored in the landfill, that happens over a period of years. So we design each phase maybe for 1 or 2 years each phase. So we only work with that part of the landfill. So as you can see, these are the phases of the landfill. Then there are pre-treatment areas. If I want to do some sort of sorting of the waste, some amount of recycling, that could be done. So that's a pre-treatment area. So it's a big center over here. Then we could use a compactor, so that which before we put in the garbage, we can first compact it and then we can put it inside. So that's why we can install a compactor over here. Then we have a leachate collection and treatment system, a gas collection and treatment system, a stormwater pond, which is required for surface water management. And we have a control building, weigh bridges for the weighing the particular vehicles. There is an entry gate. There is an operational building, workshop, where repairs could be done, garbage building, some sort of other processing could be done and so on. So typical facilities within a waste, landfill site. Typical facilities within this landfill site area includes access roads, equipment shelters, weighing scales, office space, waste inspection and transfer station, temporary waste storage or disposal sites, for special domestic hazardous waste maybe, areas for waste processing, maybe shredding of waste, demarcation of the sanitary landfill areas and areas for stockpiling, where we can stockpile some amount of material like cover material and liner material, storage, drainage facilities, sanitary landfill gas management facilities, leachate treatment facilities, monitoring wells, tire cleaning units for the waste collection vehicles, because once it moves out of the site, if the tire is dirty, it will keep on spilling the garbage in the normal urban roads. That is not desired. So that's why tire cleaning units are also installed. So these are the typical facilities in the landfill site. So landfill site is not only about storing of the waste or the volume required for waste storage, but also several allied facilities also needs to be accounted for. So we have discussed that base is excavated as per the predetermined phasing plan. So we have to discuss on the phasing of that particular landfill site, and then accordingly the base has to be prepared. Now, because these phases are done not simultaneously one after another, but the bases are also, at the end of the day, the bases has to be integrated so that there is no leakage in between these two bases, right? So because of the two phases, we have got the bases which are constructed at two different time periods. So there may be some gaps in between this. So that should be prevented. So integrity of the base layer should be maintained. And waste fill volume, based on extent of the base and waste field contours for each phase designed for at least 1 year. So that means phases should be at least 1 year, or sometimes it could be for 2 years. And phase base for phase 2 is excavated and prepared 6 months before the final contours of phase 1 are reached. So that means we have to prepare the next phase before even the first phase is, the previous phase is completed. And in this image you can see the different ways phasing could be done. The bottom one is very simple. Phase 1 we are giving a 3:1 slope, then the phase 2 is after that, phase 3 is after that, phase 4 is after that. Why this is done this way? Because phase 4 will require separate sizes of cells, so we have to design it separately. Plus, because at the end of 1 year we can put a cover over here and protect this area so that infiltration will not happen, and we only work on this area, so this becomes the active phase. Or it could be done like this, we do phase 1 like this, then phase 2 could be done in this order, and then phase 4 could be above top. So there could be hundreds of ways we can do the phasing of a particular landfill site. So let's see a typical example of a landfill site. So first we have to determine the site boundary along with the contour lines of the site to understand where we have to cut, where we have to fill, and so on. So we have to create the subsurface profile of the site. So you can see this is the bedrock, maybe the soil layers above it, maybe there is sand, then the groundwater table we have to determine, then the layer of soil above it, maybe there is silt soil over here, right? So this is what needs to be determined, and the entire profile or the section of the ground needs to be understood. Once that is there, based on the site we can determine what should be the layout of the site. Like over here, this is the gate, this is the weighbridge, some buildings, parking, workshop and other infrastructure could be put over here. This is the actual area of the landfill. This could be again broken up into different phases. And over here we have the leachate collection system, treatment system, treatment area, the gas collection and treatment or energy generation area, or surface water management facilities and so on, all housed over at this site. In case the waste processing is happening, like we can do some amount of composting or we do some amount of other sorting. So in addition to the landfill area, we have a waste processing area also fit into the landfill site. Now this is how let us assume this is the section of the landfill, the profile of the ground. So we can go a little bit below, maybe groundwater is available even below, so we maintain the minimum distance, and we can dig up and we can go for a trench fill initially, and then as we have discussed earlier, most landfills are like a modified area landfill. So over here you can see that eventually the landfill will look like this, some part below, some part above. Now the base of the landfill is given a slope like this. As you can see over here, that is the bottommost part, the sides are sloped. So this is the side, so this aligns with this, right? So this is the side slopes are given on all the 4 sides, and the center is the base is more or less flat. But of course this again, the base, even though it's shown as a flat, the slope has to be given as per the drainage network, as we have discussed earlier. Now top of the landfill over here also, it is not, it's not a square box, it's more or less like a pyramid. So it looks something like this. Why? Because we have to give a 3:1 slope so that vehicles can go up as well as water can come down, and usually the top is relatively flat. So that is what is being shown over here. So this aligns with this. Okay. Now this could be the phases of the landfill. Again, the phase design could be in many different ways we can do the phase design, but let us assume the phases are done like 1, 2, 3, 4, 5, 6 and so on. So this is how the phasing has been done. Now once the landfill profile is designed, then we can determine that the gas collection wells, the placement of the gas collection wells. So this has to be predetermined. We can design the not only the gas collection system but also the drainage system and so on. So those layouts could be designed earlier based on the profile of the site as well as the section and so on. The top of the landfill, we can design the surface water drains, at what height we will design the drains. So this needs to be predetermined. The liners, drainage layers, covers, all can be predetermined when we design the entire landfill and before actual operation all these designs needs to be finalized. Now, in many cases, and as per instructions in the MSW, in the Solid Waste Management Rules 2016, we need to also close and rehabilitate old dump sites. How we can do that? So, let us assume this is a waste dump which is there. How we can close it? We can put a proper cover. As you can see over here, we are giving it a shape. There we can put a proper cover on the existing dump site, and here also we can put some impermeable barriers so that we prevent groundwater to come and mix with this particular dump site. So this is one way. So the other is to put a particular cover above the existing dump, and then we are done with it. In other thing, if this kind of things are not possible, we can just put at least a proper cover at the top and then close it. Now, sometimes what happens, there is also, we have discussed this earlier, that there is limited amount of area available for landfill. So sometimes we have to work with the existing landfill sites, which are maybe not properly designed. So in that case, what we can do is, we can take an existing landfill site like this, we can relocate the waste and we can regrade the landfill. So this is how we can assume that this is going to be the design of this landfill. So we can shift this waste to this site. As you can see that we are moving the waste, giving it a shape, we can put a proper cover on it, and then we can have excess area available for future waste. Or in this case, you can close this existing landfill site like this. Some amount of waste could be relocated over here, and we can have new waste, a new landfill design, fully new landfill design at the side of the existing landfill. Sometimes it could be also designed in this way, where partially it can rest on the existing landfill and partially it can be on the side of this particular landfill. So this is how existing landfill could be also redesigned, re-engineered to take care of new waste and in a more protected facility. So how do I calculate the total area required for a landfill site, right? So that is what we have to do. But as you understand, we cannot do very detailed estimate at the beginning, because we are neither aware of what sort of waste will eventually come in the future. We can make estimates, but we don't know exactly how much. What would be the condition of the site if some natural calamity has occurred. So we need to modify our designs gradually, right, over the life of the active landfill, or over the life of the landfill site, right? But before we even start, we have to determine where we should acquire land, how much amount of land should be required. So we need to do some preliminary assessment. So to do that, we have to follow certain steps. These steps are given by the Central Public Health Environmental Engineering Organization, CPHEO. So we can follow these particular steps. So these are, first we have to determine the waste generation per year, this current year. This is in tons per year for this particular urban area. And then we can assume the rate of increase of this waste, which could be 3%, 4%, whatever is the case may be. So in case this waste generation growth rate estimate is not there, in case the population growth rate can be utilized. Now, as you can understand, with more population, more waste will be formed, but that doesn't mean that exactly with growth in population, the waste will also grow in the similar way. If the growth in population is of like certain income brackets grows more, in that case, other kinds of waste would be generated, right? So that means waste generation growth has to be estimated on its own. If it is not there, then only we have to go with population growth rate estimate. So proposed life of landfill, then we have to go with the assumption of the proposed life, which may be n years, right? Then we also have to estimate that what would be the waste generated at the nth year, right? So that means at the rate of this growth, maybe 3% to 4%, 2%, whatever it is, what should be the waste that is be generated in the nth year of the life of the landfill? Why? Because the waste that is coming to the landfill will not remain same over the years. So we have to account for that. So this is given by W into 1 plus X by 1000 to the power N. N is the number of years of the site life. So this is the final year. This is the initial year. So the total waste generated over the life of the landfill is half of W plus the final year's waste multiplied by the number of number of years of site, right? So we take the average waste generated per year over this site life multiplied by the number of years of site life for this particular site. So that gives us the total waste generation in n years. Now, waste generated is not the waste volume that is required, so it depends on the density of waste. So first we determine the waste volume by dividing the total waste quantity of waste divided by the density of waste, right? So density of waste is assumed to be 0.85 tons per cubic meter. So we divide that and we get around this is the value which is the VW, or which is the volume of waste in n years. Now, total volume of daily cover which would be required for this n years is actually 10% of the total waste volume that we have discussed earlier. So we take 0.1 VW is the total waste volume is VW. So 0.1 that is 10% of that is for VDC, which is volume of daily cover, right? Not daily cover, daily cover. Then along with daily cover, we require components like liners, covers and so on, right? So total volume that is required for that, assuming a 1.5 meter thick liner system, 1 meter thick cover system, including leachate collection, gas collection layers. So in that case, we can take another 0.25% for landfills of smaller height. If the landfill is of larger height, this volume is lesser, which is 0.125, means 12.5%, or in case of 30 meter high landfills, this is even lesser, which is around 8%, right? So in most cases, it would be safe to assume a value of 0.25, and we can say that we require another 25% of the volume of waste as this sort of liners and covers that are required in a landfill site. Then these are all additions in terms of volume, but at the same point of time, volume likely to be available within 10 years due to settlement or biodegradation of waste, right? So there is a lot of organic matter in the waste which degrades, and accordingly a lot of gases are released and so on. So there is a lot of compaction that happens, right? So or settlement of the waste that happens. Usually that is taken as Vs equal to m into Vw, where the value of m is around 10% for biodegradable waste or 5% for incinerated or inert waste. So in case there is a lot of biodegradable waste, we can assume that in most Indian landfills have got certain amount of biodegradable waste. So it is safe to go with 10%, right? So that means 10% volume would be available due to compaction. So total estimate of landfill capacity is Ci equal to Vw plus Vd plus Vc minus Vs, right? So Vs is the additional volume that is available because of compaction, whereas these are additions, this is subtraction. So finally, this is the total volume of landfill. So this is the total landfill capacity that is required. We have not yet estimated the area. It depends on the height, of course. But before we do that, we have to understand the shape of the landfill that we will adopt and what would be the section of the landfill, right? How much of it will be below ground, how much of it will be above ground, or is it just a landfill which is above ground? Will it be area type, trench type, slope type, valley type, or a combination of all this, right? So based on topography of the area, depth of groundwater table and other factors, we will determine what sort of, shape what sort of landfill we will go for, and based on that, we have to determine the area. So the first assumption is that the area is restricted, right? So that means we have a fixed area for the landfill site. So we now know the volume of area that is required for the, this overall waste and, allied material volume, right? Covered volume and so on. So if we can say that 0.15% of the area would be required for the infrastructural facilities, or alternatively we can say 85% of the entire area of the site would be dedicated for storing of waste and covers and so on, right? So we take only 0.85% of the total area which is available, AR. So definitely the height of the landfill would be C1, which is the overall volume required, divided by 0.85 AR, right? So this would be 0.85 AR, sorry. So this is what we can take, right? Or instead of 85, we can take a little bit more because of, compaction and all, but we better go with 0.85. So this is the height of the area that is required, because it's not only about the waste, but also some amount of, this cover and all these things will be at the top of it. So the height would be a little bit larger. So that's why it's taken 0.9, but we can again, that depends on the actual design of the landfill site, but it would be safe to go with divide by 0.85. So that means, the height of the landfill site is determined if I know the area, but this is never the case, right? In most cases, we determine the area which is required based on the design of the height. Now, the height design is based on the profile of the section of the landfill, the groundwater table depth, and many other factors, right? Operational factors and so on. So typically it is 10 to 20 meter, and rarely sometimes it goes around 30 meters, right? So typically we have landfills around 10 to 20 meters. So in that case, the height is more or less fixed. So we fix the height beforehand, right? There may be other aesthetic concerns and other concerns as well. So in that case, Ci divided by Hi, this is Ci, gives me the total area required for the landfill. Now this area is just for the storage of waste. So in additional area required for infrastructure, we have to add another 15%, so which becomes 1.15 AI. So this is the total area that would be required for the landfill site. Now, as you understand, this is the preliminary estimation of the landfill capacity, and that also a very, very crude estimation. I will show you some examples later. But if I need to do the actual, we need to refine these estimates of the landfill capacities using landfill height, the actual height that for that particular area, and that considering the local context, we have to refine these particular estimates. So volume of daily cover, liner system and cover system is revised as per actual shape of the landfill. Because if I go with a landfill which is like this, it will require certain kind of cover. If I go with a landfill like this, it will require another, volume of cover. So, but even though the overall volume remains same. So this has to be re-estimated as per the actual shape of the landfill, and also depends on available materials for cover, liners, available soil that would be used for making this particular liners and covers. So we have to refine the estimates for landfill capacity, height and area. So final and precise estimates after topographical survey. This topographical survey is done at 0.3 meters contour intervals, and waste quantities may vary from initial estimate significantly during the operation years. So all this will lead to refinement of the landfill capacity over the years, and we need to adjust accordingly. So I will very quickly take you through a problem just to give you an idea. Again, this will demonstrate how you can also calculate, but this is not exact. You can make modifications as per your case, right? But it will give you an idea about how to go about the process. So let me first read through the problem. Design a landfill for a medium-sized city of 3.5 lakh population, and the population growth rate is 3% per annum. Per capita waste generation is 0.5 kg per day, out of which 20% of waste by volume is recycled or recovered. So that means 80% of the waste goes to the landfill site. The tentative landfill site has been identified at a distance of 12 km from the city with annual precipitation of 600 mm and sandy silt soil with groundwater at the depth of 15 meters. So that means groundwater is not an issue. That means groundwater is much below. And the soil is silty and sandy soil. Landfill life is 20 years and landfill will be operated in 10 phases, each phase lasting for 2 years. So that is what has been given to us. So what we have to estimate? We have to estimate the area and capacity of the landfill considering area fill method and standard sanitary landfill with all allied infrastructure for leachate treatment, gas collection, groundwater monitoring system. Determine the design of each phase and cells in each phase along with the volume and surface and the source of daily cover. So that means for each phase, how much amount of volume, what would be the cell size in each phase, what would be the volume required, what would be the amount of daily cover required, this has to be determined. Design the overall cross section of the landfill, and finally determine the size of the leachate collection tank. So these are the things that has been given to us. Now few assumptions or few rules that has been given to us. Each phase extends from base to final cover. So that means each phase would be done in this way. That means if I have a landfill site, something like this, right? So we don't do one above another. Volume of one phase equal to landfill capacity divided by number of phases. Area of one phase capacity divided by height of the landfill, of course. Number of daily cells 365 into landfill life divided by number of phases. 365 multiplied by landfill life into divided by number of phases. So that would be the total number of cells required in the landfill. So that every day waste comes in. So that has to be considered. Volume of one cell is equal to phase volume divided by number of cells. Area of one cell equal to cell volume divided by 2 meters. So that is given, the height of each cell is given as 2 meters. The leachate volume usually depends on the volume of precipitation, volume of the pore square liquid, the liquid that passes through the geotextile layer comes into the leachate layer, volume lost to evaporation, volume of water absorbed by waste. So this is how the leachate volume needs to be considered. But for thumb rule, we can say 25 to 50% of the precipitation from active landfill areas and 10 to 50% of precipitation from covered areas becomes leachate. So that means when we are walking on the landfill, that means we are pushing waste into the particular phase. In that particular phase, operation is going on. In that particular area, around 25 to 50% of the precipitation that falls will go inside the landfill. Why? Because we have only a limited soil cover, like 10 centimeter soil cover at the end of each day's work, right? And also there would be intermediate soil cover on the areas which are, not being worked for the next 3 months, right? But still a lot of water goes in. So because there is no final cover given, but 10 to 15% of precipitation from covered areas, that is intermediate covered areas or final covered areas, if only a limited amount of water enters from those areas. So that is around 10 to 15%. In case of final cover, this is even lesser. So as you can understand, it is very, very complicated. It needs to be as per actual design, actual state of operation. We need to determine how much amount of precipitation will go inside this particular landfill site. So going into the problems, we will follow the same procedure given by CPHEO. Population is 3.5 lakhs, per capita 0.5 kilograms per day. Current waste per yard which goes into the landfill site in tons, W tons, is 80% because 20% is recycled, so it comes to 140 tons. Rate of population growth 3%. Proposed landfill life is 20, which is N. So we can determine the total quantity of waste that is generated, which comes to around 3928 tons of waste. Now total volume of waste is in 8 years, which is this total tons of waste divided by the density, which comes to around 4621 meter cube of waste is generated, right? Then assuming lift height of 1.5 meters to 2 meters and 15 centimeter top cover, we can say that total volume of daily cover comes to around 10%, which is 462. Here you can determine the quantity of soil cover that is required and the volume of soil that is required. So 462 meter cube of soil. Total volume of other components of liners is 1155 meter cube of soil, which is 25% has been adopted. Then settlement volume 10%, and because there are two phases, it is multiplied by 2, because every 10 years we can estimate settlement, but you can ignore this 2. In that case, it would be half of this which would be available. But anyway, you can also consider a little bit higher settlement as well, because it is for 20-year period. Final estimate of landfill capacity is as per the formula given earlier, which comes to around 5315 meter cube of this space that is required. Now height is given, which is 9 meters. So area required would be total volume divided by 9, which is 590 square meters. Infrastructure facilities another 15%, so it becomes 679 square meters, right? So the total breadth of the landfill is, if I take a squarish landfill site, so it comes to around 27 meters by 27 meters. Each phase is for 2 years, number of phases is 10. We divide the volume of each phase, like total volume is 5315 for west divided by 10. This is the volume for each phase. So plan area of each phase is also then divided by 9. H is 9 because each area has been done and then we move on to the next area, right? So that is 59 square meters is the area of each phase. Because the area is 59 square meters, we can say the size of each phase, again if I consider it as a square, around 7.69 square meters for each length and breadth of each phase. Total number of cells, because it's for 2-year period, 365 into 2, 730. Height of each cell is 2. Volume of each cell is, this is the volume of one phase divided by 730. So this is the volume of each cell, and we divide by 2, we come to around 0.365 is the total area of each cell. And because it is 0.365, we can say if I consider a squarish cell, each size, each direction is 0.6 meters, right? So that is 2 feet by 2 feet is one cell. So this is a very, this shows you a very crude way to estimate the cell size eventually. But at the same time, if of course the waste volume increases, the phase volume increases, automatically the cell size would be larger. Now this is a little bit more detailed way of calculating the exact same thing. So instead over here what we have considered is, instead of assuming the waste that is coming to the landfill site for every year it is same, it is different because waste is increasing every year. So this is estimated over here. As you can see, in the 0th year waste is 140 tons, whereas in the final year waste is around 245 tons. So obviously the total volume that is required to cover for this waste is also different in the different years, right? If the total volume is different, then the area for each cell that is required would also be different. So that is what it is given here. The breadth, depth, and the for each square cell, that is would be also different. The size of the cell. This is the area of the cell. This is the length size of the cell. Cover volume would be different. Components volume would be different, liner and all. Total volume that is required is addition of all this, and yearly volume that would be also different. So phase wise volume we can determine because 2 years makes it one phase. So each phase would be of different volumes. So that means that at the end of the day, each phase will have different sizes. So that also could be computed in this particular way. So finally, we come to the design of the cross section of the total landfill site. As we have discussed, landfill is not a square. Usually it starts at a base. It could go both ways. It could be below as well as above. Let us assume that in this case, this is a area fill method, which is already mentioned. So we start at the ground, we go up, and we give a slope of 3:1, something like that, right? So over in this case, we have this the total volume is given. This is the volume of the landfill site. This height is 9 meters. Assuming a square plan, and landfill is like a truncated square pyramid. So volume of truncated square pyramid is this one, a square plus b square plus ab into h divided by 3, where a and b are the sides squares. Of course, a truncated square pyramid is a square. So the bottom base is has a length of a, the top base has a length of b. So that is what the formula is. And when we calculate it, assuming a slope of 1:3, a is equal to b plus 6. So a is b and 3. This is 3 meters on both sides. So b plus 6 is a, and we can estimate it over here. We can say that b, we can convert b, we can change b to a, replace each b with A with B plus 6, right? Because A is B plus 6 because of the slope, right? So in that case, we can calculate the value of B, which comes to around 22 meter, and if B is 22 meter, obviously A would be 28 meter. So that gives us an idea about the shape profile of this particular landfill site. Finally, coming to the leachate calculation problem. So average total precipitation is given. Only one phase is operative per year. So we have to understand how much leachate is generated per year, because the rest of the time there is cover given, and after cover there is very little amount of infiltration that happens, so that can be ignored, or that would become the part of surface water management, right? Then plan area for operating phase is different in each phase, but we can assume it's the same one, right? And we can say that based on the active area that is being operated upon, the area which is filled with intermediate cover, the precipitation's volumes would be different as per this rule. But to make it simple, we will do the calculation based on what we learnt earlier, that is, assuming 80% precipitation in a 4-month period, we will consider the peak leachate quantity that is generated. We can estimate that by multiplying the total precipitation, which is 0.600 mm. We will take 80% of that, and this is the size of each cell, each phase, the area required for each phase, and we divide it by 30 days into 4 months, and we get this is the total cubic meter of water that, or leachate that needs to be stored per day. So this is how we can estimate that, right? So we can do that by taking an average value of the active phase area that is being walked upon, and we assume that the entire area around this whatever infiltration is coming over here, that is being considered what is falls over here, and then we can do this particular estimate, because it's an active area, most of the water percolates inside, right? So based on that we can do this calculation. But anyway, so this is a much complicated calculation which could be done following water balance analysis and the health model that we have discussed earlier, but crudely we can do this kind of an estimate. Now coming to 2 case studies, we will first discuss about this landfill by the Ahmedabad Urban Development Authority at Fatehwadi in Ahmedabad. It is a shared facility of 12 Nagar Palikas of West Ahmedabad Urban Development Authority. It serves 10 lakh people every day. Around 200 tons of waste comes to this landfill site. The annual rainfall of the site is 300 mm, groundwater table depth is 6 meter, and the soil is sandy. Now what design has been done? So as you can see this image of this particular landfill site, and total disposal capacity is determined as around 50, considering 50 tons per day for 8-year period, around 1,45,534 cubic meter. This is the total disposal capacity. Landfill size designed is 151 meter into 122 meter, and the height is 7.9 meters. Amended clay liner of 900 millimeter thickness with 10% bentonite clay. HDPE liner 1.5 millimeter thick, which is standard. 300 millimeter thick protective soil cover over HDPE. Drainage layer is 300 millimeter thick with 100 millimeter protective soil cover. Leachate collection and treatment facility is via 150 millimeter dia pipes. Earlier we have learned 200 millimeter dia pipes, but here they have adopted 150 millimeter dia pipes. HDPE perforated pipes are used. Leachate collection tank is given, which is 2 meter by 2 meter into 3 meter, which is the height. Leachate is transported by tanker and discharged to a nearby trunk sewer. So that means through the sewerage network, the leachate is transported to a sewage treatment plant where it gets treated with the normal sewage. Gas collection system is via HDPE vent pipe of 230 mm diameter. And also stormwater drainage is also constructed. So this is how the landfill design has been done. Sanitary landfill design has been done by the Ahmedabad Urban Development Authority. Next, coming to another landfill design in Vizianagaram municipality, which has got 36 wards. You can see this pipe sticking out. So this is the gas collection well, a passive well, right? So this allows the gas to come out of the lower layers of waste, which is below here. So total waste generated is 120 tons per day. Average annual rainfall is 1000 to 1032 millimeter. Clay soil is available, 30% clay and 35% silt. So because of that, there is no need for separate amended soil and all these things required, which was required in the earlier case. 30 acres of land for landfill facility with 55 meter and 2 meter depth. So 10 km from Vizianagaram town and includes existing dump site yard. So already the existing yard is also there at the same location. Segregation conducted at transit point. So segregation of waste is conducted at transit point. So a clay liner is utilized using the same soil that is available in site. A HDP sheet is additionally added, which is of 1.5 millimeter thickness. Now the sheet width, each sheet is 7 meters in width, length is 140 meters, and that means each 6 rolls of 980 square meters each is required to cover this particular site. Filter media above HDP liner 0.3 meter, which is standard. The drainage layer is of 0.3 meter. It includes 20 millimeter chips and 12 millimeter chips. One is for 0.2 mm and other is for 1 mm height. So 1 feet and 2 feet. HDP pipes 160 mm, total length 200 meters. 5 numbers of pipe, each 40 meters apart, has been designed. Leachate collection and treatment is through a collection pit, 7.5 meter into 7.5 meter above, larger above, and 2.5 meter below with 2 meters depth. Right? So that is the design. Gas venting is via a chimney of 30 feet height. So that is this gas venting chimney. So this is how landfills have been designed in India. So these are some examples of them. And similarly, all landfills in future needs to have, as we have discussed, gas management system, active ones, leachate management systems, water management systems, surface groundwater systems, so on. So these are some of the references you can study. So to conclude, preliminary estimation of landfill capacity, height and area is conducted before assessment of site location. And final design of landfill depends on local context, waste collected in each phase and engineering design principles. Thank you.